Hello, everyone. Welcome to Breakout Session E. We will have three excellent presentations today. This session is about life cycle and regional assessment of transportation emissions. And we will start with the first presentation on life cycle modeling of technologies and strategies for a sustainable freight system in California. And this presentation will be given by Dr. Hanjiro Ambrose, who also spoke earlier in the day. Dr. Ambrose is an engineer with the California Air Resources Board, Office of Community Air Protection, and a researcher with the Institute of Transportation Study at UCDAVIS. I would like to welcome Dr. Ambrose for his presentation.
Thank you, Kanok, and thanks to the audience for their time today. So as Kanok mentioned, my name is Hanjiro Ambrose, and this research actually is research that I conducted while I was a PhD student at UCDAVIS. So it's sort of a different hat from this morning when I was representing the Air Resources Board. Just want to highlight that, and as well recognize that I seem to have messed up my title slide. I want to recognize my co-author on this project, Professor Alissa Kendall at the University of California, Davis. Today, just to provide an overview, I'm going to discuss some of the motivation for and goals of this research, provide an overview of the methods employed, and summarize some of the key findings, and hopefully discuss some potential next steps. So while many air quality issues that affect California are regional in nature, disadvantaged communities are disproportionately impacted by negative air pollution, and particularly near roadway sources. For example, in the Los Angeles area, which I show here, there's 5 communities that have been identified through the state's AB 617 program, which identifies communities to partner with to develop local strategies to reduce emissions and community scale exposure. And one of the key issues that we've continued to hear from communities and from local stakeholders are issues related to medium and heavy duty vehicle traffic and freight goods movements in communities. California is a leader, is recognized as a leader in climate policy and in driving the technology that I think is going to ultimately provide some significant benefits. But California also has a history of non-attainment for air quality standards. And as I mentioned, these non-attainment areas tend to particularly impact disadvantaged communities. California's freight transportation system is a vital part of the state's economy, but it's also a significant contributor to greenhouse gas emissions and generates an even higher portion of local pollution. In 2016, for example, a little less than 6% of the California vehicle fleet was heavy-duty trucks, but they represent more than 60% of NOx emissions and aerosol emissions from mobile sources. So these trucks tend to already operate in areas with poor air quality and can exacerbate existing unhealthy conditions. So the state's primary strategy for reducing emissions from on-road freight sector relies on deploying new vehicle and fuel technologies, particularly electrification of surface transportation. And electrification of heavy-duty vehicles provides an opportunity to both eliminate tailpipe emissions and also potentially reduce the total life cycle emissions, i.e. all emissions from including the emissions associated with the production of the vehicle, disposal of the vehicle, production of fuel, and as well as other impacts from vehicle operation. So the goal of this study was to quantify the life cycle costs, emissions, and benefits of in the form of reduced local health damage impacts from electrification of medium and heavy duty vehicles. The study relies on or builds upon a number of existing models and attempts to capture a wide range of vehicle vocations, designs, and duty cycles. We focused on the California context and examined a target for 100% electrification of in-state registered medium and heavy-duty vehicles, and the focus on this of the study is really on the urban distribution context. So we are not examining, we're not including trucks, Class 8 type trucks that are heavy-duty trucks that operate in long-haul context, but rather focusing in on those medium and heavy-duty vehicles that are operating in the urban center. The study, we employed a life cycle perspective on emissions from conventional and electric vehicles. And this was to ensure an appropriate accounting of displaced or shifting emissions from switching to alternative fuels. And a life cycle perspective is really critical to compare potential impacts throughout the supply chain. For EVs in particular, the production of electricity is a critical component of the emissions attributable to electric vehicle truck over its lifetime. And for that reason, our study focused on including a reflection of both current and future electricity generation in the state. And the California grid, just to illustrate, here in California compared to some of the national case, has some of the highest targets for renewable energy generation regionally, and some of the lowest, for the highest renewable generation shares today. And it's important to take this into account when thinking about the potential benefits of electrifying medium and heavy-duty trucks. So for the study, we drew the primary source of life cycle inventory data was the greenhouse gases in an energy and emissions transportation model, the GREET model, maintained by Aron National Lab. Energy and fuel price components, as well as the generation forecast, were obtained from the Energy Information Administration, or agency, apologies. And combustion emissions factors were obtained from the California Mobile Emissions Database, the MFAC model. And we used speed-weighted combustion emissions factors to capture the differences in emissions over a duty cycle. This emissions analysis was paired with a model of life cycle cost, which include pollution health damages. So pairing life cycle assessment and life cycle costing offers a robust framework for considering the costs and benefits of technology changes in the transportation sector. And the primary source of data for cost estimates here for the infrastructure costs and vehicle costs were drawn from the A-Fleet model, another model that was that's maintained by Aron National Labs. In addition to the infrastructure and technology costs, we also included potential externalities in the form of reduced pollution health damages. And these marginal pollution health damage costs in the form of $1 per ton at near ground emissions levels were obtained from the Air Pollution Emissions Experiments and Policy Analysis model, the AP2 model. So heavy-duty vehicles serve in a wide variety of vocations. They're highly customizable, including body and chassis configurations, which can be designed to support a variety of applications. And this diversity of duty cycles contributes to considerable uncertainty when estimating the costs or emissions benefits of electrification or fuel switching in general. So in order to endogenize that variability into our modeling, we evaluated a range of telematic data from fleets to characterize duty cycle characteristics, including the driving range, duration, acceleration, and stopping events. Just to illustrate here, some duty cycle data that we obtained from the fleet DNA database. And this illustrates that across different vocations, even within the same vehicle class, we could see a wide range of duty cycle requirements. So similar to the scale-tracted power approach used in some existing models like MOVES, we developed a descriptive model of vehicle duty cycles based on a specific fuel consumption metric. This allowed us to create a disaggregate view of costs and emissions reductions from electrification across this range of duty cycles, and also capture potential efficiency improvements in specific applications. And this approach also allowed us to examine the impacts of loading on fuel consumption. To illustrate here, we can see the difference of a fully loaded versus unloaded vehicle type across a range of different vocations. So this can be highly important for comparing high intensity or highly inefficient duty cycles, like those moving cargo short distances around intermodal hubs. Another unique contribution of this work was an in-depth examination of battery costs and energy storage and infrastructure costs for electric vehicles. Battery costs is a key driver of electric vehicle costs, but battery system sizing and the design of infrastructure are a kind of a jointly estimated issue and highly dependent on the duty cycle requirements. So in order to examine the energy requirements of different vocations and duty cycles, we also analyzed trip patterns and durations to identify opportunities for opportunity charging. So these opportunity charging scenarios can help inform potential futures where we have smaller battery sizes, but more available charging infrastructure, which has a trade-off in providing more efficient cargo space as we have less cargo capacity or weight capacity of the vehicle tied up in an electric vehicle battery. I'm moving quickly through to just highlight some results. I want to keep moving so we can have some time for questions, as I think discussion is often very fruitful. So I'll just highlight a few of the takeaways for this, and then obviously I encourage everyone to please provide a link to the report at the end, and please feel free, I encourage everyone to review the results themselves. So when we marry the telematic duty cycle with the life cycle well-to-pump emissions and speed-weighted emissions factors, we observe wide variability in the expected emissions rates of conventional, medium, and heavy-duty vehicles. It seems I've lost my legend here, but on this slide here on the right, in the blue are the average life cycle emissions in grams per mile for electric vehicles across the scenarios considered in this study, and compared in black to the average of conventional gasoline and diesel vehicles in that category. So the wide range of efficiencies observed, particularly within the Class A segment, contributed to increased uncertainty in the emissions from EVs. So the efficiency of the vehicles on the duty cycle, a lot of duty cycles that required relatively high energy consumption, contributed to higher uncertainty in the emissions observed from EVs. Unsurprisingly, when we look at this on a ton-mile basis, the trends tend to reverse, where smaller vehicles tend to look like higher emitting on a unit of mass transporting basis. But in general, we observed that the life cycle emissions rates of some heavy-duty vehicles in these vocations were much higher than the estimated combustion emissions rates on average assigned to that vehicle class. So today, the costs of electric, medium, and heavy-duty vehicles remain highly uncertain. And one of the big drivers of this, in addition to variability in duty cycles, is the variability in energy costs. Electricity prices can vary quite strongly across regions depending on demand charges and other types of rate structures. In California, obviously, there's been considerable amount of development on this front with collaboration between utilities and fleets on work to come to agreeable rate structures. But given the variability in rates, that can contribute to a lot of variability in the potential fuel cost savings. But as we move forward over time, the future improvements in battery cost, continued improvements in battery performance are going to shift the economics of electrification across some of these vocations. So to illustrate that, here on the right, I wanted to illustrate a couple of changes that might occur by 2030 within batteries that we assessed in the model. In particular here, we could see the potential in reduced costs for a battery system. For a Class A truck where a battery might cost as much as $100,000 today to deliver a complete duty cycle, we expect that cost to reduce by more than half by 2030. In addition, as battery costs are falling, performance is improving, which means that the amount of mass required to move the battery, as well as the amount of cargo capacity that might be lost to an additional battery system, will also decrease. And this means that electric vehicles, electric heavy and medium duty trucks, are more likely to be economical in an increasing range of applications. Importantly, there's a huge opportunity to improve, to reduce externalities from conventional vehicle operation through electrification. By 2040, electrification of Class 8 trucks alone could reduce GHG emissions by more than 50 tons annually. And electrification of medium-duty Class 3 and 4 vehicles would have significant impacts on reducing VOC and fine particulate matter emissions in certain areas. Based on our assessment, we found that statewide, if 100% of in-state urban distribution vehicles, Class 3 to 8, were electrified, we could see significant reductions in annual pollution health associated damages, somewhere between $500 million a year by 2025 and well over $1 billion by 2040. So this report is available for download, and I encourage anyone to feel free to examine it and reach out with any additional questions. There's a lot more research required to understand and improve our ability to quantify the benefits of vehicle technology and fuel switching, particularly of electrification of surface transportation in the medium and heavy duty sector. And there's also an opportunity, I think, at a finer scale to look at rerouting, geofencing, or other strategies which can help reduce exposure to conventional vehicle emissions in the meantime, while we collectively pursue a low carbon fuel system. Thank you for your time. Concludes my presentation, and this work was supported by a range of funding sources, including the National Center for Sustainable Transportation and the Lady Foundation, and the National Science Foundation. So I want to thank all the financial supporters of the work.
Thank you very much, Dr. Ambrose, for the excellent presentation. And just want to remind the audience that if you have any question, please type your question into the Q&A box on the right panel. And while we are waiting for questions from the audience, I have a quick question for you. In your almost final slide, you show that emission reduction from Class 3 combined is more than Class 8, and that is driven primarily by a reduction in VOC. Can you comment on that a little bit?
Yeah, that had to do a bit with the pollution health damage weighting, in that because of the trade-off in secondary fine particulate matter between whether you're NOx limited or VOC limited in certain regions, VOC emissions reductions can result in significant pollution health damage reductions, as VOCs can be a significant contributor to secondary fine particulate matter. Now, in certain areas, gasoline-powered Class 3, which is a large share of the medium and heavy-duty vehicle fleet that operates in-state, is registered in-state, those vehicles are responsible for a large share of VOC emissions, primarily from evaporative emissions and non-operative emissions. And by reducing those VOC emissions, we could see significant health damage savings.
Okay, thank you very much. Yeah, look like there's no other question from the audience. So yeah, I would like to thank Dr. Ambrose again for the presentation. And then, sorry, one just come in. Does the health damage include potential hazards of battery waste from battery trucks?
That's an excellent question. I appreciate that, particularly as I do a lot of work on battery recycling, actually. No, we did not include end-of-life processing for batteries. It's still, I think, a system that needs to, that has a lot of uncertainty in understanding what pathways will exist for battery recycling. You know, just to mention, though, that, you know, lithium-ion batteries, while while a durable good that will need to be recycled and possess and contain a lot of critical minerals that we will need to maintain supply of, they don't pose the same toxicity issues that some other chemistries of electrochemical storage have, like lead acid batteries. And so it's important to note that while there's obviously opportunities for creating a robust recycling system that adheres to the highest standards for environmental health and safety, there's a difference, I think, between lithium-ion batteries at their end of life and electrochemical storage like lead acid batteries.
All right, very good. Thank you again. Okay, so I think we're gonna go to the next presentation, which is regional assessment of implementing autonomous vehicle dedicated lanes on transportation congestion and emissions. And this will be presented by Ms. Farinoush Sharifi. She is a doctoral student in transportation engineering at Texas A&M University and an assistant researcher with CAR-T. Her primary research interest lies in utilizing data analytic techniques in developing data architectures and practical solutions for a more sustainable transportation system. All right, welcome, Farinoush.
Thank you. Hello, everyone. I'm Farinoush. I'm an assistant researcher at CAR-T, and today I'm presenting a regional full chain assessment of dedicated AV lanes using our developed tool, PATH. As Dr. Zitzman mentioned yesterday in the keynote sessions, the interaction of the infrastructure and air quality and health is an area that needs further research to help decision makers make more informed decisions, especially considering the continuously changing state of the transportation infrastructure because of the new technologies. One of these new technologies is autonomous vehicles, and they are known for their improved safety and reduced time headways between vehicles. So AV lanes are introduced as an effective tool to improve the capacity of the lane and at the same time boost the market penetrations for the AVs. However, random deployment of these AV lanes over the region may not necessarily improve the performance of the network or even compromise the performance at very early stages of the penetration. Therefore, we need a full assessment of the regional operation improvements of AV lanes at different AV penetration levels. And as referring to my points earlier, we need to assess the health impacts and the health interaction with this infrastructure and these improvements. Our study's goals were first to incorporate the AV demand activity into the current travel demand model, and second to conduct the dedicated AV lane and construct the configurations into the existing roadway network. Finally, we wanted to assess the environmental and societal role of dedicated AV lanes at both regional and boundary project levels. So we assessed the greenhouse gas emissions and other criteria, pollutant emissions as the environmental assessment, and we studied the health impacts or the asthma cases attributable to traffic-related air pollution as the societal impact of dedicated AV lanes. So our case study was done in El Paso. El Paso is located on the southwestern part of the Texas, and it's a major freight hub with several ports of entry to Mexico. So there is a high traffic activity and truck activity in this region, and El Paso is designated as a non-attainment area for particulate matter 10 according to the National Ambient Air Quality Standards. So every transportation project happening in this region needs a vital emission and health assessment. So on the right map, you can see the corridor that we selected for this study is part of the I-10 from loop 375 to downtown El Paso, and it's selected because of the major traffic congestion and high demand at this corridor level. So in our study, first, we needed to set up the network configurations. For that purpose, we removed one general purpose lane from that corridor and added a new dedicated AV lane, which is like an access managed lane with access before and after any exit or entrance ramps. So the next step for the network setup was to update the traffic flow model in response to the improved car following model for the autonomous vehicles. So we improved the speed from the 60 mile per hour to 70 mile per hour. Next setup point was to set the demand for the autonomous vehicles. We replaced some of the light-duty conventional vehicles with light-duty autonomous vehicles at 3 penetrations rates, 1%, 5%, and 10%. So you can see the four scenarios here in the table, and the baseline has 0 penetration rate, and the highest penetration rate is 10%. Then we used our platform to assess transportation health and sustainability toolpath to assess the environmental and health impact of each scenario. PATH is a cloud-based modeling modeling platform for automating and integrating transportation emission and energy models. The pipeline first gets the travel demand models and adjusts them using our penetration rates for autonomous vehicles. Later, we use these demands to generate the network congestion using the dynamic traffic assignment. Then we generate the link level emissions using the moves matrix and the network congestion, and we assess the pollutant dispersion using AirMod. Finally, using the health impact studies, we assess the asthma cases attributable to traffic-related air pollution at each neighborhood. Each of scenario has been conducted 5 times to include the significance of the environmental and health impacts. So this table shows our corridor level traffic operation and emission impacts and their significance as shown as the p-values. As you can see, the network congestion has been significantly reduced for all penetration levels, and it was even more reduced for high penetration levels, showing that at the earliest stages of the autonomous vehicle penetration, there are still some congestion over the general purpose lane, but while once the penetration gets higher, there are more autonomous vehicles, they can use the facility for higher speed. Also here in the higher adoption, higher penetration, you can see some of the vehicles were rerouting from other alternative routes to this I-10 corridor. According to the table, we cannot really capture any significant improvements in greenhouse gas emission or particulate matter emissions. So these charts show our regional traffic operation and emission impacts. As you can see, we can observe congestion relief at the high penetration of the AVs. But again, we cannot see any greenhouse gas or particulate matter changes over the whole region. So truly the the dedicated AV lanes for any penetration levels, they can be a congestion relief at both corridor level and regional level, but they are not really a climate change tool. But we can see some localized impacts over the spatial maps. As you can see here, VMT is very varied. It's mostly because of the stochasticity of the network. And translating into the network congestion, you can observe some changes over the upstream or downstream of the corridor. The corridor is here. And there are also some changes over the alternate routes. These are also translated into the emissions, greenhouse gas emission and PM2.5. And you can again see the changes over the corridor, the changes at the upstream or downstream, and some changes at the alternate routes. And port of entries to Mexico are here. It's around the border, so it's a very major area. Again, translating it into the dispersion and attributable asthma cases, we can see some changes at different splits of the corridor, some changes, localized changes at the alternate routes, at the downstream and upstream, and at around the border. So in this study, we assessed the environmental impacts and environmental and health impacts of the dedicated AV lane, and environmental impacts were assessed using the greenhouse gas emissions and criteria air pollutants. And societal impacts were also assessed in terms of health impacts or asthma cases. Significant congestion reduction was observed at both corridor level and regional level, and no significant changes was observed for the regional emission. However, we could observe some localized emission and health changes, asthma cases changes in our spatial map. So dedicated AV lane is really an effective tool for congestion relief while changing the flow pattern for the emission and health. Dedicated AV lanes are actually lane management plan, and they manage the lane by assigning the access. So like all other lane management plans, they are a viable option for congestion relief. They cannot be counted as a climate change tool. And still we can observe some changes over the local neighborhoods in the emission and health impacts. However, zero emission AV lanes may promote the zero emission AV penetration in the region more, and they may have different implications if we study those cases. I would like to thank you all for attending my presentation today, and appreciate the team behind this research. And you can visit our website and dashboard, and please let me know if you have any questions. Thank you.
All right. Yeah. Thank you very much, Farinoush, for very interesting work. We have a couple of questions from the audience. The first one is, which GHG emissions were looked at as part of this work?
It's the CO2 equivalent, so it includes the greenhouse. It includes both CO2 and other, I say, CH, and I cannot have it on my mind, but it includes all greenhouse gas emissions, including the smaller portions. So it's the CO2 equivalent.
Okay, thank you. Okay. Another question is, do you include construction in your analysis? And this refer to emissions from concrete and other building materials? Or do you assume that the land already exists and it is converted?
No, we actually didn't consider the well-to-wheel, so it's just the emission from the over a day of commuting over the network. And what we have done is we just we built a new lane we built a new way without considering the emission from the construction for the baseline. We let all the vehicles access that lane in the baseline scenarios, and during other scenarios, other penetration scenarios, we just block them from accessing them and letting just the autonomous vehicles use the access. So there is no well-to-wheel emission calculator, just from after that.
Okay, thank you. We still have time for more questions if anyone would like to ask Farinoush question. In the meantime, I have one quick question. So in the modeling, the fleet characteristic of AV in terms of their emission profiles, was it assumed to be the same as the other regular LDV?
Yes, it was assumed to be a light-duty vehicle, and as I said, different like zero emission, say zero emission, or different hybrid ones. They may have other implications, but the fleet distribution was considered to be the same as the light-duty fleet distribution.
Okay, yeah, thank you. All right, so if there is no other question, yeah, I would like to give Farinoush an applause for the excellent presentation, and then yeah, we will go to the last but not least presentation. And our next presentation is energy use of full electric and combustion engine vehicles in transient traffic. And it will be presented by Dr. Aron Jazcilevich. He is a researcher at the Center for Atmospheric Science at the Universidad Nacional, Autónoma de Mexico. His main research topics are air pollution modeling, individual pollution exposure, vehicular emissions, and energy use. All right. Welcome, Dr. Jazcilevich. You are currently muted. Yeah, okay.
Oh, sorry. Can you see my presentation? Can you see my presentation now?
We see your screen.
Perfect.
But, we saw the presentation a minute ago when you actually shared it.
Okay, perfect. So here it is. Can you see it now?
Yes, but can you do? Yeah, that view is perfect.
Perfect. Thank you very much. Well, my name is Aron Jazcilevich. I'm a researcher at the Center of Atmospheric Sciences at the National University in Mexico. And today I'm going to be presenting you a paper on energy use of full electric and combustion engine vehicles in transient traffic. And well, as we know, transient traffic is a malady that exists all over the world, in the United States, in Asia, and of course, in the city where I live is Mexico City. Well, transient traffic, stop-and-go traffic, is a ubiquitous feature of daily urban life. As motorization grows, this phenomenon is certainly going to grow even more. Larger portions of commuter time will be spent under these conditions, consuming energy and aggravating emissions. Since transient traffic includes sharp braking and short accelerations, usually after a long idling time, important fine-scale dynamics must be included in the analysis. There are a lot of events that happen in very short time that have to be included in order to capture all the dynamics of this type of traffic regime. Also, this traffic regime is difficult to reproduce by a driver, even in under controlled conditions in a laboratory. And if you try to circumvent this problem by averaging, then important dynamics might disappear. In today's presentation, I'm going to have a different approach from what previously was presented, in that my approach is microscopic. That means I'm going to be following car by car, vehicle by vehicle, at 1 second time scale. And this microscopic approach is especially tailored to study transient traffic. Basically, this scheme is based on an observational technique using video tracking analysis to capture necessary high-resolution dynamics, as I will show. Two, an agent-based traffic model, SUMO, to obtain high-fidelity driving cycles, and it's a microscopic agent-based traffic model. Number three, we pair all these to a complex vehicle simulator to obtain energy use, fuel consumption, and emissions of vehicle, while the car, in advisor, is following SUMO's traffic as one of the many cars that are immersed in SUMO's generated traffic. Advisor is being substituted by autonomy. Those both are models generated by the Department of Energy, Aron laboratories. Some preliminary results will be shown. I'll use conventional electric vehicles to exemplify the scheme. The scene where we apply all this scheme is on a hump in a street, because therefore we can use a theoretical model, a theoretical MMD traffic queuing model that we can compare our results, besides, of course, with the measurements. And once this is accomplished, that we know all our scheme, our system is working fine, we then vary the flow scenarios and observe the corresponding energy and emissions behavior. So what about the video tracking observational technique? Well, we use a drone in order to obtain the video of the place where we are going to be observing the traffic. And this is the output of Kinovia tracking system, in which you can see that we are able to obtain the velocity of the vehicles, the instant velocity, quite well characterized. Every second we are able to obtain the instant velocity of all vehicles passing through the hump, which is not very well marked. So when you drive in Mexico City, be very careful. But the important thing is that you can obtain the instant velocity in quite very accurately using this video tracking technique. Also, you can obtain the flow, traffic flow characterization, different type of vehicles that are passing through your scene, through your window. And you can also check how is the lanes distribution. This is going to be important for when you apply a queuing theory. And of course, you can obtain the hump crossing speed of all the vehicles that are going through. Well, all this information that you obtain by video tracking, especially dynamic data, is very important in order to obtain good results with the microscopic agent-based SUMO traffic model. To the right, you can see what will be the results for different car flows, traffic flows, 1,000 cars per hour, 2,000 cars per hour, and what will be the length of the queue being formed behind the hump. Okay, according to theory in blue, in MMDQ in traffic flow theory is in blue, and you can see how Sumo is able to reproduce quite well the theory. This is using the dynamic data that you were able to capture using Kinovia. Whereas if you will be using only the velocimeter, you would observe that no queue is being formed. So you have to have very good dynamic data in order for Sumo to be working. You can have a further explanation here. This is the velocity that we recorded with the velocimeter. And this in gray is the cloud of observations just before the speed hump and a little bit afterwards in gray. And in blue, you have all the traffic generated by Sumo. And you can see that Sumo is able to reproduce quite well the observations. Okay, that is in gray. In blue is Sumo, which means that it's working very well. This is thanks that we incorporated the right dynamics. Once we know that our model is working well, our traffic model is working well, we then start varying, and we are confident that it's working well, we vary the traffic flow in order to obtain our different scenarios. This is an output of Sumo, in which we have the cars crossing where we want to observe the traffic, but where this traffic in Sumo is characterized with the right amount of each type of cars that are entering. This is our border where all the different cars are entering. So we're able to simulate the traffic where we want with the right traffic characterization. I'm going to show you one more graph, which I think it's interesting. And this is where we are where we want to simulate our traffic. Here is the hump. But since Sumo is an agent model, a microscopic agent model, we can also simulate pedestrians and different type of pedestrians. If we put the right dynamic data, we can simulate adults, the way they walk, and children. And we compare then our simulations with traffic. This is red because the bus is just stopped before the hump, all right? And once they go away from the hump, they acquire another color because they're going faster. Okay, I think Sumo is quite neat to use. Then we have thousands of driving cycles generated by Sumo, and we hope it's correct with the correct dynamics, and we put them into a simulator. This simulator, we're going to try to change it to Autonomy, but meanwhile, we're using Advisor of the Department of Energy, and from Sumo, we put the thousands of driving cycles that were generated by Sumo, and at the end of the simulator, we can obtain the emissions, the fuel usage, and all kinds of other parameters. Of course, each of these boxes contains a lot of information about the gearbox, about the weight of the car, etc., etc. In order to be able to simulate these cars, the fuel converter, we must obtain experimental data for the fuel converter. And the experimental data is RPM against torque, and in the third dimension, in this case, the efficiency of the motor. We can substitute this by an emission three-dimensional map. And instead of this, you will have what is the emission of, for example, NOx at 2,500 RPMs and 50 Newton meter torque. All right. So we could use different maps. That's what is the core of simulation in Sumo. And for the electric car, we obtain this map, 3D map RPM, torque against efficiency for the S3 Tesla car. By the way, the conventional car we used is a Ford EcoSport owned by my institution that we use for our experiments. One neat thing about Advisor is that you can obtain the emissions, place the emissions where they happen, because we have emissions every second, for each of the different scenarios, traffic flow scenarios. For example, when the queue is already formed behind the speed hump, well, you can place where are the emissions taking place. And when there is no hump, when there is no queue, well, this is where the car goes. This is for one car. Each car, you can follow every single agent. This is for one car, where you can place where the emissions are. I think this could be interesting for roadside exposure studies. This way, you can, if you go on one of the Sumos, follow one of the Sumos cars, you can obtain what are the changing emissions before for the different scenarios, and you can obtain a comparison as traffic flow grows. What are the emissions in the window that you're observing? Also, you can do the same thing for energy expenditures when you put as a reference point the situation, the scenario when there is no queue, and compare it when the queue is growing, and obtain what's difference, a sensitivity analysis of different technologies that you may use to do this comparison. We found, besides that, of course, electric vehicles spend much less energy than conventional cars. This sensitivity we obtained that electric vehicles are much less sensitive to the growth of the queue, and that's I think it's important for as transient traffic grows. We can now know that electric vehicles are less sensitive than conventional cars to transient traffic. As a conclusion, by coupling Sumo and Advisor, the energy use of EVs and CVs, electric vehicles and conventional vehicles, was obtained under reproducible queuing traffic scenarios. And I stress the word reproducible. This was only possible by introducing a video traffic technique in order to obtain essential dynamics, not possible using GPS or a velocimeter. Energy evaluation of traffic scenarios and salient features were thus able to obtain. So you have a model, you can reproduce and do how many scenarios as you want. And among the traffic salient features is that we are able to obtain the energy expenditure for different technologies and also their sensitivity to traffic buildup. Okay. Well, as a free announcement, I'm going to end up this talk by showing you quickly the things that we do at my institution. We would like to have, of course, more complex situations. This is a more complex situation to obtain also the energy expenditures for using for each agent different type of technologies, electric cars, hybrid cars, etc., etc. We also do CFD. This is 2 buildings and how the emissions of PM2.5 distribute in urban canyon using different turbulent parameterizations. We also measure exposure to passengers in different systems, traffic transportation systems. This is here an example. And we are spending a lot of time now to obtain data and modeling road exposure. And this is just some photographs of one of our latest campaign. I would like to, of course, acknowledge the government of the Mexico City that provided us with funds to do our research, of course, to our drone operators. And if you need some references, you can see my presentation. Okay, I think with that I finish.
Thank you so much, Dr. Jazcilevich, for the very interesting presentation. Look like there's a lot of interesting work happening at your institution.
Thank you.
So, all right, I'm looking at Q&A box. All right, so yeah, we're still waiting for a question from the audience to come in. In the meantime, I have a quick question for you. So, the finding that electric vehicles, energy consumption of electric vehicles is less sensitive to the Q. Was it because some of the energy was recouped by regenerative braking?
Since you're using a advisor, you can follow all the systems of the car. We found that since the velocities are very low, there is not enough kinetic energy to recover energy, okay, by braking. Okay, so that where regenerative braking is not particularly good in that type of traffic because there is not much kinetic energy to obtain energy. So, and it uses less energy because a conventional car has to spend energy just to be in idle, whereas an electric vehicle always spends its energy when it's stopped. Only have your radio on, and so it doesn't spend that much energy.
Oh, thank you. All right, we still have a few more minutes for Q&A. If anyone has additional questions.
May I ask a question, Aron? I was curious about auxiliary loads for vehicles, actually, and how you treated that.
All is taken care in autonomy and in or in advisor. There is you can specify air conditioning. You can specify auxiliary loads. You can put your own estimate, or you can one of the modules you can put as a module. You can put air conditioning, and also now that you mentioned that. You were concerned about weight, you know, when you explained your talk, how things change with weight. You can also change your weight, and dynamically, you can put some weight in certain part of the cycle, and then change the weight for another part of the cycle. You can do all those changes in advisor or autonomy.
Yeah, I'm familiar with advisor. I just was curious, you know, how you reflected auxiliary loads specifically for the fleet composition you were looking at, given that you had, you know, a reflection of vehicle traffic and sort of some case examples for light and medium duty vehicles within that. Particularly when you said that, you know, that the stop and go traffic with, you know, as you mentioned, I was just curious about the auxiliary load because, you know, as you were, I'm sure aware that sometimes those auxiliary loads are quite substantial.
Yes, and it varies the emissions. When you turn on your air conditioner, especially in a small car, you can change the emissions, and because the motor can run hotter or cooler, and your emissions change, especially of NOx, and that is taken care in advisor or autonomy.
All right. And yeah, we have a few more minutes left, so I would like to open the floor to questions for any of our speakers. So if anyone has additional questions for any of our speakers, please feel free to post it in the Q&A box. Yeah, but so far, yeah, this has been very interesting session. So we see everything from life cycle assessment to macroscopic transportation modeling, and then down to microscopic vehicle simulation. So we cover all the bases. Very interesting work. Okay, I think yeah, there's no other question from the audience, and if you can think of any other question later and would like to reach out to any other speaker, I think there's a speaker lounge that you can get in touch with them. And I would like to take this opportunity to thank all the speaker again for all the excellent presentation, and also thank you the audience for participating. I hope you enjoy the rest of the day. All right, bye bye.
Thank you very much. It was a
Thank
pleasure.
you. Yes,
Thank
absolutely. Thank you.
All right.
Enjoy the rest of symposium.
Yes, hope so. Okay.